Okay, so we're now going to go back and fill in the remaining steps of this history-based approach to parsing. Remember, the first step is to somehow represent trees as sequences of decisions, and that's what I've just shown you on the previous slides. The second step is to say that the probability of a tree is, by the chain rule, a product of terms where at each point I condition the ith decision on the entire sentence as input and the previous I-1 decisions. So the remaining steps of this approach are going to be to derive a log linear model that estimates these conditional distributions, and finally to somehow implement search for the highest probability parse tree. So let's talk about this next. How do we use a log linear model to define this conditional probability? So the basic idea is rather simple, actually. Following the usual definition in log linear models, this conditional probability is going to be e raised to the power f dot v, where f is some feature vector and v is some parameter vector, divided by a normalization constant where I sum out all of my decisions. So notice here I have f, which is a feature vector that looks at a history in combination with the outcome di. So the history in this case considers the entire sentence s and the previous I-1 decisions. And the outcome, of course, is the dith decision. Similarly, if I look at the denominator, I have a sum over all possible decisions at this point in the parse tree. So we use script A to refer to the set of possible decisions at this point that we're considering. So f is going to be a function that takes a history outcome pair and maps it to a feature vector. And v is going to be a parameter vector. And of course, we're going to take f of all this context, inner product with v, exponentiate it, and then normalize in the usual way we've seen for log linear models. So let's think a little bit more about this feature vector. It could potentially look at any information in the history in combination with the decision outcome at this point. Remember, the history consists of a sentence and a sequence of I-1 decisions. This, in fact, is going to correspond to some partially built structure. Okay, so we may have some structure like this, maybe with some starts and various other pieces of structure. At each point in those slides I showed you previously with the decisions, we have some decision that we need to be made. So let's say, for the sake of argument, we're trying to make a decision over this constituent. And we could potentially condition on any information in the surrounding sentence or in the previously built structure, the part of speech tags, the chunks, and so on that I've built. So again, we're going to leverage the flexibility of log linear models in defining quite rich features that can look at the decision being made in conjunction with the contextual information. So the big question is, how do we define these features f? And so I'm just going to give a brief sketch of the kind of features that Ratnapaki used in his particular parser. So the feature vector definition can vary depending on whether the next decision falls into the 4 different classes I've basically shown you on the previous slides. So it can vary depending on whether I have a tagging decision next, a chunking decision, or one of these start join decisions at the stage after chunking, or a check equals no versus check equals yes decision. And so he actually developed different feature vector definitions for each of these 4 cases. Very briefly, for the tagging decisions, he used exactly the same features as we've seen before for part of speech tagging. So he basically used exactly the same approach as for the part of speech tagging case. For the chunking decisions, he used very, very similar decisions. very, very similar features, which again considered the word being chunked, spelling features of the word being chunked, the previous word, the next word, the previous two chunking decisions, and so on. Really, these features mirrored the features used for part-of-speech tagging. The only subtlety with these features is that they can themselves look back at the tagging decisions. So I could ask questions about what is the part-of-speech tag for the current word that I'm trying to chunk. That obviously is a very useful feature. Let me now give a sketch of the features used with these join or start decisions. So we can look at head words, we can look at constituent labels, we can look at start join annotations, all considering the nth tree relative to the decision being made, where n considers the previous two constituents. That's the choice that Ratnapaki made. So these head words are recovered using the head finding rules that we saw right at the start of the class on lexicalized PCFGs. And so we'll assume that we do have these lexical items available. They can be useful. But in addition, we can look at constituent labels, part-of-speech tag labels, and so on. Similarly, we can look ahead. So we can look at the head word, constituent label, relative to the decision at position 0. That is actually the current tree being built upon, and also 1 position ahead and 2 positions ahead. So to give a sketch, if I have some set of subtrees, some of them have join or start annotations, and then I'm trying to make the decision here, I can look at the non-terminal label here, the part-of-speech tag here, non-terminal label here, the head words of each of these constituents, and similarly I can do this for the previous 2 constituents. He also looked at bigram features, which might join information here between these 2 constituents, or here between these 2 constituents, or trigram features, which would look at 3 sequences of label 3, where we might look at the 3 non-terminal labels along here, or the 3 non-terminal labels here, or the 3 non-terminal labels here. Finally, we might look at various punctuation features, because punctuation is often very useful in parsing. Things like commas, colons, semicolons, the presence of those in the neighborhood of a decision can be quite useful in disambiguating these parse trees and in deciding which decision to take. So this is really just a sketch. The main point I'm trying to get across here is that when we make this decision, join or start, at a particular constituent, we can employ quite rich representations of the context surrounding that decision. For the check decision, there are 2 choices, either check equals no or check equals yes. And so we might, for example, if we had check equals yes right at the start of the parse tree I showed you earlier, we might have constructed this parse tree here, which is actually a rather bad parse tree fragment. Whereas, so this is check equals yes. If I'd chosen check equals no, I would have left this as a start S, and we would have had this kind of structure. So for these check decisions, Ratnapaki used a set of features which asked a variety of questions about the constituent which would be built if check equals yes. So we might, for example, have a feature saying, well, in this case, I've constructed a rule, S goes to NP. And presumably, by the way, this is bad. This is an indicator that something's gone wrong, and so this feature should get a negative weight. We might ask a variety of other questions about the constituent that I've constructed through this check operation. So that's it for basically the feature vector definitions in Ratnapaki's model. That's a fairly high-level sketch of the type of features he used. Once those feature vectors have been defined, we can train the parameters of the log linear model in the usual way, using typically some kind of regularized maximum likelihood approach. basically using an identical algorithm to the one we saw for training the parameters in general log linear models, or specifically in the log linear models for tagging. Again, I'll stress that one nice thing about these models is that we can make use of quite rich representations, quite rich feature vector definitions. Now remember, in part-of-speech tagging, we made this Markov assumption that the jth tag depended only on the previous two tags in addition to the entire sentence. But in the parsing problem, I've in general made use of features that might be sensitive to all kinds of decisions that are made in the past. That's because when I was making this decision here, I wanted to condition on all kinds of context in the past, in the future part-of-speech tagging and chunking decisions. And so this kind of Markov assumption doesn't really make sense, or at least it would be very limiting in the case of parsing. Now, because this decision di could depend on arbitrary decisions in the past, because I do not make an independence assumption like this one, this really means that dynamic programming is going to be out of the question, because it doesn't, the decoding problem does not have the required structure for dynamic programming, i.e. it does not have some kind of Markov structure. So instead, Ratnaparkar used a beam search method, very similar to the beam search method that you saw for phrase-based translation decoding. I won't go into the details, but intuitively, this is going to build several possible parse trees, left to right, using the kind of decisions we just described. Each of these parse trees is going to have some probability. And at each point, we'll just keep around, say, the top 20 or 30 most probable parse trees under the model for that partial set of decisions that I've made in constructing each one of those parse trees.